Okay, start with that. So we'll get the x dy, that will equal cosh y. So that means dy dx equals 1 over cosh y. What are we trying to get to? I forgot. Uh, oh yeah, so then that means the derivative of y, which is sine inverse x, that will equal 1 over cosh y, which is cosh sine inverse x. Um, is that what they want us to do? Um, so let's see if there's an identity we can use, though. Hmm. Yeah, maybe we should use that formula. So that would equal 1 over root 1 plus sine inverse squared. So it'd be 1 plus x squared. So you need to use then the formula. Yeah, the cos is root 1 plus the sine squared. So that checks out. Okay. 430. That's going to be something similar, isn't it? So you'll get dx dy equals sine y. So that means dy dx is 1 over sine cosh. Um, and then we can use the formula sine cos squared minus 1 root cos squared minus 1. So that'd be 1 over root x squared minus 1. Is that the right formula? Derivative of cos inverse. Yes, it is. Okay. Prove the formula for the derivative by differentiation. Okay, so we get the same thing again. We'll get the derivative of sec inverse x will be 1 over the derivative of sec derivative of sec is sectan. not x, sorry, y. So that would be 1 over minus sec inverse x. And then it's tan sec inverse x. So we need a formula for that. What's the one? We have cos squared minus sine squared equals 1. Divide by cos squared, so that's 1 minus tan squared equals the sec squared. So the tan is root 1 minus the sec squared. So that'll be root 1 minus the x squared. So is that the formula for sec inverse? Minus 1, yeah, x root 1 plus x squared. Ah, made a sign mistake. No, it's right. But there's a minus. Yeah, no, that's right. That's right. That's right. But it has to be the absolute of x. Okay. Right. Prove that equals that. Maybe we could prove it by derivatives. So if we differentiate the left, we'll get n cos x plus sine x power n minus 1. And then the n comes out. No, maybe that's not the best way. I think I'll have to do a proof by induction, perhaps, which isn't in this book, or binomial expansion, which also isn't in this book. Let's try proof by induction. So the proof by induction goes, okay, so step 1 is case n0. So, or maybe we should start at n1, actually, the first case. So that's obviously true. That's clearly true. Then step 2, we want to assume it's true for k. No, well, I can do this, but then I'll have to use more trig identities. No, I'll use the binomial. That's what I'll do. Okay. So I'll just say cos esh plus sine esh n, which I'll just simplify a little bit as cos plus sine n. So that's cos n plus, okay, nc0 cos n sine 0 plus nc1 cos n minus 1 sine 1, and then it continues all the way down to ncn cos 0 sine n. So Hmm. Let me pause and think. I've been thinking about I don't know if this is the best way to do it, but it's a way to do it. So if you say y equals cos x plus sine x power n, and if you differentiate this n times, um, the n would come down and would come down again, come down again. So you'd end up with n factorial y. Now, if you were to take this one, and if you differentiate, the n comes out, and the n comes out, and you're left with the original. Oh, it's not n factorial. It's n. So we'll call that m. So the n comes down m times, and if you differentiate this one m times, the n comes out, the n comes out again, the n comes out again. So you'll end up with this times the original. So they both solve the same equation. So except for a constant, must be the same. Yeah. I mean, you could make the m1, and so if they both solve it, you just need to show that the c is the same. They're both the same initial value. So on the left, y0 will be hyper cos 0 plus hyper sine 0. Power n. So it's 1. And the same goes here. Y0 equals 1. So they both solve the same equation, and y0 equals 1 for both. So then that means that they have to be the same. And that's probably the easiest way to do it. Yep, that's probably the easiest way to do it.